Good morning. Today I am here to discuss my project topic on the my project on the topic a survey of various electrode materials for supercapacitors with special reference to conducting polymers. Introduction. A supercapacitor is a pulse current system that is used to meet high current and specific power requirements for duration less than 1 minute. Supercapacitor is used as energy storage option to improve power efficiency and enhance the cycle life for applications such as hybrid vehicles, cranes, elevators, etc. This figure shows a comparison of energy storage devices such as supercapacitors, batteries, and fuel cells. And here we can see the supercapacitors compared to other energy storage devices show a higher specific energy and specific power. The performance of supercapacitors are significantly affected by electrode materials, choice of electrolyte, and the potential window of their electrode. This is a comparison between batteries and supercapacitors through different operational parameters such as storage mechanism, power limitation, energy storage, charge rate, and charge life limitations. As you can see, the energy storage mechanism is chemical in batteries, whereas it is physical in supercapacitors. And also the charge rate. Charge rate is kinetically limited in batteries, but in supercapacitors, it is high as the discharge rate. And the charge life is very high for batteries, for supercapacitors compared to batteries. And charge life is 1 million hour to 30,000 hour for batteries, whereas it's only 500 hours to supercapacitors, sorry, for batteries. And the operating temperature for supercapacitors is 40 to 100 degrees Celsius, whereas for batteries it is only 20 to 60 degrees Celsius. To enable electronics with high flexibility, the corresponding energy storage devices, such as batteries or supercapacitors, must be featured with small volume, lightweight, and high energy or power density. This review mainly focused on the electrode materials for supercapacitor fabrication with special reference to conducting polymers. And here we also discuss the strategies to achieve high stretchability, high rate performance, stable cycles, and also the challenges faced in this emerging field. Energy storage mechanisms in supercapacitors. The principle of operation of supercapacitors is mainly based on energy storage mechanism, and on the basis of this, there are three types of capacitive behaviors: electric double layer capacitors, pseudocapacitors, and hybrid capacitors. This figure shows the taxonomy of supercapacitors, such as the classification of supercapacitors as EDLCs, hybrid, and pseudocapacitors. And EDLCs include activated carbon, carbon nanotubes, and graphenes. And pseudocapacitors include metal oxides and conducting polymers. And hybrid capacitors include the composite hybrid, asymmetric hybrid, and battery type hybrid. Here, first we can discuss EDLCs or electric double layer capacitors. Electric double layer capacitors or EDLCs. EDLCs consist of two carbon-based electrode materials, electrolyte and a separator. They store charge either electrostatically or via the non-Faradic process. The principle of energy storage is electric double layer. Here, when a voltage is applied between the electrodes, the charges accumulate at the surface of electrode. And also, due to this potential difference, the ions of the electrolyte will get deposited on the oppositely charged electrode. Here, to avoid the recombination of ions, an electric double layer is formed. When the specific surface area is increased and the distance between the electrode is decreased, then EDLCs attain higher energy density. EDLCs also have high cycle stability compared to batteries. Next one is pseudocapacitors. Pseudocapacitors store charge via Faraday process. That means there is a transfer of charge between the electrode and electrolyte. Here, when a voltage is applied, the reduction and oxidation takes place at the surface of the electrode material that lead to the passage of charge through the electric double layer. As a result, current is flowed through the supercapacitor cell. Due to this Faraday current, pseudocapacitors have greater specific capacitance and energy density than EDLCs. Examples are metal oxides and conducting polymers. Hybrid supercapacitors. It is a combination of both EDLCs and supercapacitors. Hybrid capacitor is formed by combining the energy source of battery-like electrode with a power source of capacitor-like electrode in the same cell. There are three different types of hybrid supercapacitors. They are composite, asymmetric, and battery type. These hybrid supercapacitors have greater cycle stability, power performances, and high specific capacitance compared to ideal and pseudocapacitors. First one is composite hybrid. Composite hybrid electrode combines carbon materials with either metal oxides or conducting polymers within the same electrode. That is, a single electrode will contain both physical and chemical energy storage mechanism. Carbon materials offers good cycle stability and electric double layer, whereas pseudocapacitors offer high specific capacitance for the composite electrode. There are two types of composite hybrids called binary and ternary. Binary uses a combination of two electrode materials in a single electrode, whereas ternary uses combination of three electrode materials in a single electrode. Next one is asymmetric hybrid. It combines EDLCs with a pseudocapacitor electrode. They are set up in such a way that carbon material is used as a negative electrode and metal oxide or conducting polymer is used as a positive electrode. That is unlike the composite. Here, two electrode materials are used in two electrodes. And next is battery type. It is made by combining a supercapacitor electrode with a battery electrode. That is, it utilizes both the properties of supercapacitors as well as batteries. Next, we are going to discuss about electrode materials that are used for the fabrication of supercapacitors. First one is carbon materials. Carbon in various forms are used as supercapacitor electrodes due to its high specific surface area, availability, low cost, established electrode production technologies. The energy storage mechanism of carbon materials, as we have discussed earlier, is electric double layer. The important factors influencing the electrochemical performance of carbon materials are high specific surface area, pore shape and structure, pore size distribution, surface functionality, electrical conductivity, etc. These factors increases the specific capacitance of carbon materials. The next widely used carbon material is activated carbon. They are also widely used electrode material and have a large surface area and moderate cost. Activated carbon is produced by physical or chemical activation of various carbonaceous material. Carbonaceous materials like wood, coal, nutshells, etc. Here, the physical activation include the treatment of carbon precursors at a high temperature of 700 to 1200 degrees Celsius in the presence of oxidizing gases like steam, CO2, air. And the chemical activation include the treatment of carbon precursors at low temperature of 400 to 700 degrees Celsius using activating agents such as sodium hydroxide, potassium hydroxide, phosphoric acid, etc. This activated carbon has a wide pore size distribution as micropores, mesopores, and macropores. A number of researchers on activated carbon tested the relationship between specific surface area and specific capacitance, but they observed a discrepancy between them. That is, at a high specific surface area of 3000 meters square per gram, a low capacitance was observed. That is, it shows that all the pores are not effective during the charge accumulation. And that is, other than specific surface area, the factors affecting the specific capacitance of the carbon materials is pore size distribution. Besides that, the excessive activation also lead to the low energy density and low conductivity. Next carbon material is carbon nanotubes or CNT. This discovery of CNTs has led to a great advancement in science and engineering of carbon material. CNTs has main advantages to be used as electrode materials in supercapacitors because of its unique pore structuring, good mechanical and thermal stability, superior electrical properties. And CNT produced by catalytic decomposition of some hydrocarbons. CNTs have interconnected mesopores. These mesopores allows the charge continuous charge distribution in the CNTs, and also it increases the it helps to increase the specific capacitance of CNT based electrodes. There are two types of CNTs, single walled and multi-walled CNTs. And CNTs are used in high power electrode materials due to good electrical conductivity and readily accessible surface area. And CNTs have small specific surface area compared to activated carbon, and therefore they have low energy density compared to activated carbon. Next carbon material is graphene. Graphene has significant importance in using as electrode materials as it has high electrical conductivity, chemical stability, large surface area, and moreover, it doesn't depend on the pore distribution like other carbon materials. Compared to carbon materials, graphene has high specific surface area of 2630 meters square per gram and a specific capacitance of 550 farad per gram. To increase the specific surface area and specific capacitance, these graphene sheets are prevented from restacking themselves during the graphene preparation and consequent electrode preparation. And to avoid this, a curved graphene sheets are used. Graphene can be prepared in many ways, such as chemical vapor deposition, arc discharge method, chemical and intercalation methods in graphene, chemical exfoliation of graphite, etc. And among all these methods, large specific capacitance is obtained by chemical exfoliation method. Next materials used for electrode preparation is metal oxides. Metal oxides are another alternative used for electrode preparation of supercapacitors, and they give high specific capacitance and low resistance. It is very simple construction of supercapacitors with high energy and power and low cost of production and uses milder electrolyte. Example of metal oxides are nickel oxide, ruthenium dioxide, manganese oxide, etc. Next one is conducting polymers. Conducting polymers are widely researched as electrode materials for the fabrication of supercapacitors due to its low cost, easy production, relatively high conductivity, and high capacitance. Conducting polymers have different electrode configuration. Example, the N or P type configuration, one electrode is negative or N doped and other electrode is positive or P doped. The charge storage mechanism in conducting polymers is reduction oxidation process. During oxidation, the ions are transferred into the polymer backbone and during the reduction it is released back into the solution. This oxidation and reduction causes a repeated swelling and shrinking of this um, material and it causes a mechanical strain in the polymer and it causes the collapse of the polymer structure and it decreases the cycle stability of the conducting polymer based supercapacitors. To overcome this problem, the conducting polymers are combined with electrode materials or metal oxides to increase their cycle stability. Examples of conducting polymers are polyaniline, polypyrrole, polythiophene, and its derivatives. Next is nanocomposite based electrode materials. First one is carbon-carbon composite. The capacitance of carbon materials depends on their specific surface area. In the case of graphene, restacking due to van der Waals interaction during the reduction process is avoided by inserting single-walled CNTs as spaces. This creates an intrapores within them and it increases the specific surface area that is accessible to the electrolyte. That increases the specific capacitance also. And the capacitance of 261 farad per gram and energy density 123 watt-hour per kilogram were obtained for graphene supercapacitors at a potential of 3.7 volt. Next is carbon metal oxide composite. A comparison was made between pure CNTs and MnO2 and the composite of MnO2 CNT. MnO2 CNT composite electrode exhibited high specific capacitance than pure CNT and MnO2. In MnO2 CNT composite, the vertically aligned CNTs show higher specific capacitance than the random ones. An asymmetric supercapacitor was made with MnO2 and graphene. This composite of MnO2 graphene used as cathode and pure graphene was used as anode and a higher specific capacitance and energy density was observed in this composite than in its pure forms. The three different composites by in situ polymerizations are first one graphene nanosheet polyaniline composite that shown specific capacitance of 1046 farad per gram and graphene nanosheet CNT polyaniline shows a composite shown 1035 farad per gram specific capacitance and CNT polyaniline shown as 750 farad per gram. Then among this higher specific capacitance is shown by GNS polyaniline composite. And the cycle stability is seen as that is after 1000 cycles, the capacitance decreased only 6% for the GNS CNT polyaniline composite and 52% for GNS polyaniline and 67% for CNT polyaniline composite. Conducting polymer based stretchable and flexible supercapacitors. The studies on electronic sensors, flexible robots, and wearable sensors recently composed a noticeable trend towards wearable electronic devices. To enable electronics with reliable stretchability and flexibility, the corresponding energy storage devices should be featured with small volume, lightweight, and high energy density. All solid-state supercapacitors have superior stretchability by packaging into sandwich type or twisted into fiber shape. In sandwich type, it is made by sandwiching gel electrolyte between two active electrodes. And in fiber shaped twisting, the hydrogel electrolyte is wrapped in the electrode. Conducting polymers are used as active electrode materials in stretchable supercapacitors due to its high capacitance, good flexibility, excellent conductivity, lightweight, low cost, etc. The only restriction is the decrease in the longevity of the devices due to the decrease in their cycle stability. Here, this graph shows the increase in the conducting polymer-based flexible supercapacitors as well as conducting polymer-based supercapacitors, and their growth year by year growth is given. From here, we can understand that compared to conducting polymer-based supercapacitors, conducting polymer-based flexible supercapacitors growth is a little bit slower, but it is there's an advancement in its growth year by year. To increase the cycle stability of stretchable supercapacitors, the substrate we have two methods. First one is addition of substrates of excellent mechanical property and high conductivity, and second is the using combinations of conducting polymers with other metal oxides or carbon materials. First, we can discuss about the addition of substrates with the conducting polymers. The conducting polymers that could be easily deposited on this substrate are used for the fabrication of stretchable supercapacitors. And these substrates should have high mechanical property, good conductivity, and high stretchability. And most commonly used substrates are polydimethyl siloxane and elastic fibers. This schematic diagram shows the fabrication of stretchable steel mesh with polypyrrole deposition. That is, here stretchable steel mesh is used as the substrate. And the second figure, or figure B, shows the flexible all-in-one configuration, all-in-one configured supercapacitor, flexible supercapacitor. And this shows the specific capacitance, the rate and cycle performance of microstructured polyaniline. This shows a high specific capacitance and also a high cycle stability also. These supercapacitors show good flexibility, good electrical conductivity, and good cycle stability. And another most common method for the design of stretchable supercapacitors is by using composite with the other materials. Polyaniline. That is, there are many conducting polymers that are used for the fabrication of stretchable supercapacitors. One is polyaniline. It is frequently used low-cost positive electrode material and high specific pseudocapacitance. It is synthesized by chemical or electrochemical oxidation by various substrates. The synthesis of nanostructured polyaniline with a sodium alginate composite showed higher specific capacitance than pure polyaniline. And this is a graph showing the specific energy density of pure polyaniline and polyaniline sodium alginate composite. That we can see that polyaniline sodium alginate composite showed a high energy density, and consequently they also show a high specific capacitance. The electropolymerized polyaniline showed higher specific capacitance of 2300 farad per gram with cycle stability up to 1000 cycles than chemically polymerized polyaniline. Polyaniline nanorods with a nano spacing showed ultra high specific capacitance of around 3407 farad per gram. Generally, polyaniline based supercapacitors show very impressive specific capacitance, although with a limited cycle stability. Next one is polypyrrole. Polypyrrole is one of the most promising p-type conducting polymers due to its unique features such as high conductivity, fast charge discharge mechanism, good thermal stability, low cost, high energy density. Electrochemical behavior of polypyrrole depends on its effective surface area and electrode preparation method. Cross-linked polypyrrole showed high specific capacitance due to high porosity and diffusivity, whereas denser and thicker growth of polypyrrole showed low capacitance due to its less porosity. The polypyrrole carbon composite by chemical oxidation method achieve a specific capacitance of 433 farad per gram. Compared to other nanostructures, polypyrrole nanostructure showed higher specific capacitance of 586 farad per gram. This figure shows a synthesis of polypyrrole nanostructures by electropolymerization and the corresponding nanostructures obtained at different voltages. These nanobelts, nanobricks, and nanosheets are the different nanostructures of polypyrrole and obtained at electropolymerization of 50 millivolt, 100 millivolt, and 200 millivolt voltages. Polypyrrole paper composite flexible electrode shows a capacitance of 0.2 farad per centimeter square, and the conductance of polypyrrole coated paper remained even after 100 cycles. Hence, this electrode is produced large scale for energy storage application and flexible electronics. Significant development is needed to achieve very high capacitance in this area. Next one is polythiophene and its derivatives. Polythiophene can be both N-type and P-type electrode. Generally, they show low conductivity and low specific capacitance compared to conducting polymers, but they have a higher potential window, which helps to make an asymmetric type supercapacitor device. Poly 3,4 ethylene dioxythiophene, PEPT poly 3,4 fluorophenyl thiophene, PMET polymethyl thiophene, PDTT poly diteno 3,4 B34 D thiophene are commonly used thiophene based polymers. A new conducting polymer is reported, which is PTTPA, polytristhiophene phenylamine. This PTTPA based electrode shows high specific capacitance of 950 plus or minus 40 farad per gram. And the specific capacitance per cycle and cycle stability is shown in this graph. We can see that the pure TTPA showed a lower specific capacitance, whereas a combination of MET and PTTPA shows a higher specific capacitance and a higher cycle stability. Besides this, ultra-thin polythiophene films with a porous activated carbon nanosheet increase the specific capacitance by 50%. This is carbon nanotube based composite. The CNT conducting polymer composite give high cycle stability as well as increased performance of supercapacitor electrode. Conductive polymers are attached to CNTs via pi-pi interaction, and the synthesis of polyaniline single-walled CNT specific capacitance is 463 farad per gram, and as well whereas the polyaniline multi-walled CNT composite give a specific capacitance of 606 farad per gram. The fabrication of unique CNT polypyrrole core shell sponge made by highly compressible electrode with a high performance give a specific capacitance of 300 farad per gram. Next is graphene or graphene oxide based composites. Graphene or conducting polymer based composites have given high specific capacitance. Polyaniline nanostructures deposited on graphene give a specific capacitance of 550 farad per gram. Graphene oxide and polypyrrole, that is GeoPPY nanocomposite film, achieved a very high capacitance, and this figure shows the graphene polypyrrole composite based flexible supercapacitors. And a composite of reduced graphene oxide and polypyrrole is reported, that is RGO-PPY combination, and this composite achieved aerial capacitance of 175 millifarad per centimeter square and excellent cycle stability. The recent study on composite graphene hydrogel and polyaniline, that is OGH PANI composite, high specific capacitance and long cycle stability is obtained. In this OGH polyaniline composite, as the content of polyaniline increased, the specific capacitance is drastically decreased. But it has a high cycle stability up to 10,000 cycles. That is shown in the figure. That is, as the content of polyaniline is increased, we can see a drastic decrease in the specific capacitance of polyaniline, and but there is a constant capacitance retention is constant even after 10,000 cycles. So this is a promising approach towards the development of high flexible supercapacitors. Here is a comparison of various electrode materials and their specific capacitance and their energy density, power density, and their stability. That is here, as we can observe, the highest specific capacitance is shown by MnO2 PeDOT composite, that is metal oxide and polythiophene derivative composite and that showed 1670 millifarad per centimeter square specific capacitance. And it has shown a cycle stability of 0.5 percentage loss after 4000 cycles. And energy density 1.80 milliwatt hour per centimeter cube. And also the graphene polyaniline paper electrode material show no loss after 1500 cycles, that is it has a high cycle stability. Conclusion: the invention of supercapacitor opened an alternative energy storage devices because of its high power density, good stability, high capacitance. Supercapacitors are bringing a revolution in flexible electronics due to the great flexibility of electrode materials. But we still need many improvements in this area to increase the specific capacitance. Also, in the case of conducting polymers, the main challenge faced is the swelling and shrinking due to continuous charging and discharging, and the subsequent collapse of the polymer structure and loss of its cycle stability. These challenges had to be overcome by combining the conducting polymers with a suitable other electrode materials. This review discusses a recent development covering some of the successful and promising works achieving high specific capacitance based on conducting polymers. Thank you.